This is the final video where we discuss spinors as members of Clifford algebras. In the previous video, we discussed how spinors are members of minimal left ideals in Clifford algebras. The easiest way to get a minimal left ideal is to find a minimal projector or idempotent element that creates a minimal left ideal. In this video, we're going to talk about nilpotent elements, which are elements that square to 0, and we'll see how nilpotents can create projectors, which can then create minimal left ideals for us. I'm also going to discuss maximally isotropic subspaces and their relationship to minimal left ideals. We'll see that, as an isotropic subspace gets bigger and bigger, the corresponding ideal will get smaller and smaller. Now, to start this video, I'm going to talk about a concept in quantum mechanics called creation and annihilation operators. These operators are used to create and destroy particles in multi-particle quantum mechanics and quantum field theory. I don't expect you to be too familiar with this, but I've left some links in the description to videos that discuss them in more detail. If you've ever studied the quantum harmonic oscillator, you'll know that one way to solve for the energy levels is to use the so-called raising and lowering operators, also called ladder operators. These can be used to travel between the various quantized energy states of the oscillator. Also, the commutator of the raising and lowering operators equals 1. When we upgrade to multi-particle quantum mechanics, we get similar operators that allow us to create particles and destroy or annihilate particles, and they obey a similar commutation relation. These operators work for particles called bosons. The defining property of bosons is that multiple bosons are allowed to occupy the same quantum state. The photon is an example of a boson. The other main category of particles is fermions. The defining property of fermions is that they obey the Pauli exclusion principle, which says that two fermions cannot exist in the same state at the same time. Matter-type particles like quarks, electrons, and neutrinos are examples of fermions. Now, let's look at the operators related to creating and destroying fermions. So with fermions, we only have two valid states, the empty state and the full or occupied state, which has a particle in it. We'll say that the operator alpha plus is the creation operator that takes the empty state and creates a fermion particle, giving us the full or occupied state. So alpha plus acting on the empty state gives us the full state. Conversely, we'll say the operator alpha minus is the annihilation operator. It takes the full state, destroys the fermion particle, and returns the empty state. So alpha minus acting on the full state gives us the empty state. Now, what would happen if we apply the creation operator to the full state? Creating another fermion would imply we have two fermions in the same state, which is impossible. So we say this is equal to 0. This 0 indicates that the probability of getting two or more fermions in the same state is 0. Similarly, when we apply the annihilation operator to the empty state, this would imply we have less than 0 particles, which is impossible. So we say that this equals 0 as well. If we examine these rules a little more, we get some interesting results. What happens when we apply the creation operator twice to the empty state? The first operator fills the state, and the second operator just gives us 0. And if we apply two creation operators to the full state, we immediately get 0 as a result. So regardless of the initial state, applying the creation operator twice gives us 0. The same is true for applying the annihilation operator twice. Applying two annihilation operators to the full state, the first one empties the state, and the second one gives 0. And applying two annihilation operators to the empty state gives us 0 immediately. So applying two annihilation operators always gives 0. So both alpha plus and alpha minus square to 0. We say an operator that squares to 0 is called nilpotent. So both the creation and annihilation operators for fermions are nilpotent. You might also see elements with this property called isotropic or null, although this language is more often used in the case of vectors. Another interesting property involves the anti-commutator of alpha minus and alpha plus. The anti-commutator is usually denoted with these curly braces, and represents adding the products of the two operators in the forwards and backwards directions. Let's apply the anti-commutator to the empty state. We distribute and get two terms. For the first term, we create on the empty state to get full, and then destroy full to get empty again. On the second term, we destroy the empty state, so we get 0. Overall, applying the anti-commutator to the empty state just gives us the empty state again. Now let's apply the anti-commutator to the full state. Again, we get two terms. In the first term, we try creating on the full state, so we get 0. In the second term, we destroy the full state to get empty, and then create to get full again. So the anti-commutator acting on the full state gives us the full state. What this means is that the anti-commutator of alpha minus and alpha plus equals 1, because whichever state we apply it to is just returned to us without any changes. We can also express the nilpotents of alpha minus and alpha plus in terms of anti-commutators, by saying that the anti-commutator of alpha minus with itself is 0, and the anti-commutator of alpha plus with itself is 0. These three anti-commutation relations fully describe the creation and annihilation operators for fermions. Now, what can we do with this? It turns out that the nilpotent operators we just discovered, the creation and annihilation operators for fermions, can be used to build projectors that give us minimal left ideals in Clifford algebras. When we take these nilpotent elements and form their anti-commutator, we see it gives 1. It turns out that the two terms in the anti-commutator are orthogonal projector partners that sum to 1, similar to the projectors we've come across in the last couple videos. If you like, you can pause the video and try to prove that each of these two elements are projectors. That is, they square to themselves. But I'm going to go ahead and prove it now. Let's take P plus, which equals alpha minus alpha plus, and show that it squares to itself. We get a product of 4 operators, and we can take the inner alpha plus alpha minus, and notice that it matches this term in our anti-commutation relation. This means we can rewrite it as 1 minus alpha plus. After we distribute, the first term becomes alpha minus alpha plus, and the second term has alpha minus twice, which immediately goes to 0 since it's nilpotent. So we end up with alpha minus alpha plus, which is the original projector P plus. So P plus does square to itself, meaning that P plus is a projector. We can use a similar proof to show that P minus is a projector. You can also pause and try to show that P plus and P minus are orthogonal. That is, their product in either direction is 0. P plus times P minus gives us alpha plus twice in the middle, which goes to 0 because it's nilpotent. And in the other direction, P minus times P plus, alpha minus twice in the middle goes to 0 because it's nilpotent. So using our nilpotent elements, alpha minus and alpha plus, we're able to define two orthogonal projectors, P plus and P minus, that sum to 1. Before, we defined projectors by finding an element U in our Clifford algebra that squared to plus 1, and then using the formula 1/2 times 1 plus U to define a projector. But now we have an alternative method for constructing projectors that uses nilpotents that anti-commute to 1. So to sum everything up, we have two nilpotents, alpha minus and alpha plus, that square to 0, and also anti-commute to 1. We can use these nilpotents to define projectors P plus and P minus, which square to themselves. These projectors are orthogonal and multiply with each other to give 0. We can also reinterpret this anti-commutation relation to mean that the two orthogonal projectors sum to 1. So all of this so far might seem a bit abstract. We've been talking about nilpotents and projectors in abstract terms, but I haven't yet connected this back to Clifford algebras. To get a concrete example, let's look at the spacetime algebra CL13, where the basis vector gamma t squares to plus 1, and the basis vectors gammas x, y, z all square to minus 1, and all the basis vectors anti-commute with each other. Vectors in space-time that point along the directions of light beams are called light-like vectors, and these light-like vectors square to 0. For this reason, we also say that light-like vectors are null, isotropic, or nilpotent. A simple light-like vector is gamma t plus gamma z. It's easy to see this vector squares to 0. The inner terms cancel because they anti-commute, and the outer terms become 1 minus 1, which goes to 0. So this light-like vector can be thought of as a nilpotent element. The vector gamma t minus gamma z, which represents a light beam pointing in the minus z direction, also squares to 0. For reasons that we'll see later, I'm going to multiply both of these vectors by 1/2. This doesn't change the fact that they're nilpotent. I'm going to call these two vectors alpha plus and alpha minus. We can check that the product of these nilpotent elements give projectors. We'll define P plus as alpha minus times alpha plus. Expanding all this out, we get 1/2 times 1 plus gamma t gamma z. This gamma t gamma z bivector squares to plus 1, so this looks like the projectors we're familiar with from previous videos. We also define P minus to be alpha plus times alpha minus. This gives us the complementary projector 1/2 times 1 minus gamma t gamma z. It's easy to see that when we add these two projectors, we get 1. Or equivalently, the anti-commutator of our two nilpotents is 1. This is why we multiplied our nilpotents by a factor of 1/2. We wanted to make sure the anti-commutator gave us 1 instead of 4. So let's review what we've done here. We started with our spacetime algebra CL13. Then we found a pair of nilpotent elements, alpha plus and alpha minus, that anti-commute to 1. We then used the products of these nilpotents to give us projectors. We can now use one of these projectors to give us a left ideal by multiplying the entire algebra onto the projector from the left, a procedure we talked about in the previous two videos. However, we saw in the last video that one projector in CL13 is not enough to give us a minimal ideal. There are still smaller ideals inside our current ideal, so we need to find another projector to make our ideal even smaller. We can do this by finding another pair of nilpotent elements. I'm going to choose beta plus, which is 1/2 times I gamma x plus gamma y, and beta minus, which is 1/2 times I gamma x minus gamma y. You can go ahead and check for yourself that these elements square to 0, and also anti-commute to 1. Another important property is that the betas anti-commute with the alphas, so we can swap the order of an alpha and a beta in exchange for a negative sign. The reason this is important is because it means projectors built from alphas and projectors built from betas will commute with each other. Remember, the reason we care about commuting projectors is because the product of commuting projectors is also a projector. If we define the projectors Q plus and Q minus using the products of the betas, we get these projectors that we saw in the previous video. If we multiply P plus and Q plus, we can rewrite the projectors out in terms of our alpha and beta nilpotents. We can then swap beta minus over in exchange for two negative signs, and then swap beta plus over in exchange for two negative signs. Overall, there is no sign change, and we've managed to swap the order of the alphas and betas, which means we've swapped the order of our projectors. So just to make this clear, when we build projectors from pairs of nilpotents, where the nilpotents between the pairs anti-commute with each other, we end up with projectors that commute with each other. Now we can take our ideal, produced by P+, and multiply it onto the commuting projector Q+. This gives us an even smaller ideal, which in fact happens to be a minimal ideal. So this is where spinors live in the space-time algebra. Okay, let's go over this procedure again from the beginning, and this time I'm going to explain how this relates to the concept of maximally isotropic subspaces. Remember, the general procedure for building spinors is to find a pair of nilpotents that anti-commute to 1, then use them to build projectors, then use the projectors to project out an ideal from our algebra. However, we need to remember that spinors live in a minimal ideal, an ideal set in our algebra that contains no subideals inside of it, except for the trivial ideal consisting of just the zero element. Let's say that we find a projector that gives us an ideal, but the ideal is not minimal because it has a non-trivial ideal inside of it. This means we need to continue using more and more projectors to shrink our ideal so that it's smaller and smaller until we reach a minimal ideal. So let's start with our nilpotents, alpha plus and alpha minus, that we've shown here. I've already said that nilpotent vectors are also called isotropic vectors. So we can think of our nilpotent vector, alpha plus, as spanning an isotropic space, which is a space where all elements square to 0. This space is just a line since it only has one basis vector. Or more technically, since we're allowing for complex scaling coefficients, we can think of our isotropic space as one complex dimensional, visualized as the complex plane. Now, if we use these nilpotents to build a projector, we get an ideal. But it's not a minimal ideal, so we need another projector to make our ideal smaller. Another way of saying this is that we need to make our isotropic subspace bigger. We need more nilpotents so that we can make more projectors so that we can make our ideal smaller. So we introduce nilpotents beta plus and beta minus. Now we can take our isotropic subspace spanned by alpha plus and expand it by including the span of beta plus. This isotropic subspace is now 2 complex dimensional. Also, a key property is that the basis vectors for this space, alpha plus and beta plus, anti-commute with each other. Another way of saying this is that the alpha plus and beta plus vectors are orthogonal basis vectors, since in Clifford algebras, orthogonal vectors anti-commute with each other. Remember, this makes it so that the resulting projectors commute with each other. The fact that alpha plus and beta plus anti-commute also ensures that every vector in their span is also isotropic. If we take any linear combination of alpha plus and beta plus and multiply it by itself, the outer terms go to 0 because the vectors are isotropic, and the inner terms go to 0 by the anti-commutation property, so we get 0 overall. So this anti-commuting property of the isotropic basis vectors ensures every vector in this subspace is also isotropic, hence the name isotropic subspace. Using our expanded isotropic subspace, we can build more projectors, which give us a smaller ideal. And in fact, this smaller ideal is a minimal ideal in CL13. So it turns out that the isotropic subspace we've built here is a maximally isotropic subspace. It's the largest possible isotropic subspace we can build inside this Clifford algebra. So the rule is, we start with nilpotents from an isotropic subspace in our Clifford algebra, then use them to build a projector to get an ideal. If we need a smaller ideal, we expand our isotropic subspace to get another projector to get a smaller ideal. The larger our isotropic subspace, the smaller our ideal. We keep expanding our isotropic subspace until we reach a maximally isotropic subspace, which means we can produce the smallest possible ideal, which is a minimal left ideal. So the key idea from this video is, in order to build minimal left ideals where spinors live, we need to build projectors using nilpotents from a maximally isotropic subspace. So let's generalize this procedure to a general Clifford algebra. Let's start with CLN0 with complex coefficients, where all our basis vectors square to +1. Let's assume that we have an even number of basis vectors. We can build nilpotents by grouping the basis vectors into pairs. The elements 1/2 times sigma 1 plus I sigma 2 and 1/2 times sigma 1 minus I sigma 2 are nilpotents that anticommute to 1. We can build more nilpotent pairs that anticommute to 1 using similar formulas, making sure that no basis vectors are used in more than one pair. Note that all the alpha pluses and alpha minuses from different pairs anticommute with each other. This means that all the alphas from different pairs are mutually orthogonal with each other. This means that the set of alpha pluses form an orthogonal basis for our maximally isotropic subspace. We use all our nilpotents to build projectors, and we multiply all our projectors together to get a minimal projector, which gives us a minimal left ideal, which is where spinors live. Now, what about CLPQ with complex coefficients? Here, vectors can square to +1 or -1. So how do we build nilpotents here? Our nilpotents will always take this form, as 1/2 times a sum or difference of two vectors. The first vector must square to +1, and the second vector must square to -1. So if both vectors square to +1, then the second vector needs a factor of the complex I, so it squares to -1. If the first vector squares to +1 and the second vector squares to -1, we can just leave them as they are with no complex factors. If the first vector squares to -1 and the second vector squares to +1, then both vectors need factors of the complex I. And if both vectors square to -1, then the first vector needs a factor of the complex I. Other than that, the steps are the exact same. Build a maximally isotropic subspace from the nilpotents, use the nilpotents to build a minimal projector, and use the projector to get a minimal left ideal where spinors live. Now, note that this procedure only works in Clifford algebras, where P plus Q is an even number, because we need an even number of basis vectors to build pairs of nilpotent elements. Let's finish off this video with a concrete example of building spinors in CL20 with complex coefficients. CL20 is not a very big Clifford algebra. It has one scalar, two vectors, and one bivector. We can scale by complex coefficients, so you can think of this as 4 complex dimensional or 8 real dimensional. This actually ends up being equivalent to CL30 with real coefficients under this isomorphism. We can build our pair of nilpotents that anticommute to 1 as follows. We can then use the nilpotents to build these projectors. When we apply our 4 complex dimensional algebra onto P12+ from the left, we end up with a minimal left ideal that is 2 complex dimensional, It is spanned by our projector and sigma 1 times our projector. So we can build spinors as linear combinations with these two basis elements. Also notice that we can take sigma 1 times the projector and use a bunch of algebra to rewrite it as alpha plus times the projector. This is an equivalent way of writing our spinor components. This gives us a two-component spinor in Cl20C. You might notice that the first component looks a little bit like an empty fermion state, and the second component looks a bit like a filled fermion state. Cole-Fury makes note of this fact as well in her playlist, when she refers to this as a Fock space. However, at this point, I don't see any reason to literally view these components as filled and empty states. This mathematical analogy with fermions is just something I used to help us understand nilpotents better. As far as I'm concerned, these are just two basis spinors used to make a spinor in Cl20. They're not actual filled or empty states. If we go to higher dimensions, the basis elements for spinors will include all possible combinations of nilpotents acting on the projector. So this is the last video that discusses spinors in terms of Clifford algebras. I realize a lot of the concepts in the last few videos have been very abstract, but learning them is helpful for working with spinors in arbitrary dimensions. Hopefully these videos will make it easier to understand textbooks and papers that talk about minimal left ideals and maximally isotropic subspaces. You can also check out this playlist by Cole-Fury, which helped me understand how nilpotents can be used to build projectors, and how projectors give us spinors. I've linked it in the description. In the next video, we'll start talking about how Lie groups and Lie algebras relate to spinors.